Every password you type, every text you send, and every bank transfer you make is currently hidden behind a math-based wall. We rely on complex algorithms to scramble our data into unreadable noise, hoping that the lock is too difficult to pick. The problem is that math is not an absolute barrier. It is an arms race. If you build a lock out of numbers, it is only secure until someone else develops a better algorithm or finds a shortcut to the solution. This cycle began with the earliest computers. As mainframes grew more powerful, we had to make our encryption more complex just to keep pace. We are essentially running as fast as we can just to stay in the same place. To end this race, we have to look past the software. We have to stop relying on the difficulty of a calculation and start relying on the laws that govern matter itself. True security requires a shift in perspective, moving away from a system that is mathematically difficult to hack toward one that is physically impossible to observe. To understand how a physical law can stop a hacker, we have to look at how light behaves at the subatomic scale. Here, individual particles, like photons, do not actually possess a fixed state until someone measures them. Before being observed, a photon exists in superposition, exploring multiple potential paths simultaneously as a spread-out wave. But the moment you try to measure it, that wave collapses. The act of observation forces the photon to choose a single, definite state. In the quantum realm, looking at something is not a passive act. It is a physical interaction that forces the target into a new state simply because you chose to interact with it. For decades, this was just a bizarre quirk of physics. But researchers eventually realized they could engineer this glitch into a security feature called quantum key distribution. One of the most effective methods is the BB84 protocol. Here, a sender and a receiver build a secret encryption key by exchanging a stream of individual, isolated photons. The sender forces photons into specific geometric shapes to represent a secret key. If a hacker intercepts this stream, the measurement creates a physical collision, mutating them into corrupted shapes. The receiver detects this instantly, and the compromised key is thrown away. The laws of physics ensure that any attempt to steal this data leaves a visible mark on the data itself, making stealthy eavesdropping an absolute physical impossibility. This isn't science fiction. These protocols have moved out of the lab and into the real world, becoming the foundation for a new kind of hardware. Engineers are now using lasers to write these quantum circuits directly into glass chips. These devices are designed to power secure networks that don't rely on the strength of a password, but on the behavior of light. This marks a massive shift from the early 20th century. When the founders of quantum mechanics first debated these ideas, they were considered philosophical problems, not engineering solutions. Early paradoxes, the thought experiments involving cats in boxes or particles that seemed to communicate instantly, were originally meant to highlight how strange the theory was. Now, those same paradoxes are the blueprints for our most secure systems. Today, this theory is being bolted into server racks. We are deploying physical quantum hardware in our modern infrastructure to protect the future of the internet. The universe refuses to be observed without consequence, and by weaponizing that refusal, we have turned a century-old scientific mystery into the most secure lock we have ever built.